Hey, I'm John. I'm a professional MCAT tutor and resident in plastic surgery. Before I went to medical school, I had to take the MCAT 4 times before I figured it out. Then I worked for some of the big national companies, tutoring students and showing them what I'm about to walk you through. If you want to see myself or the co-tutor on this channel go through all of the AAMC full-length exam questions and passages and break them down, click the first link in the bio. Thanks for watching. Hope you learned something.
Let's take a look at AAMC CP1. So I'm going to read through the passage, flowchart it all out. If you don't know what that is, that's our strategy for how we map out the passage. I'm going to focus on the basic sciences and the relationships as well. I'll highlight some of the basic sciences and I'll bring them up if I think that they're high yield. And after that, I'm going to walk you through all the questions and discuss with you how I would break down each question stem and how to get to the correct answer. Let's jump into it. First thing I do for every passage is I look to see if there's a title. There is not one on this passage, so then we jump into the reading. It says, in order to understand the chemical evolution of life, scientists have studied the production of amino acids under conditions that simulate those of primitive Earth. All right, so that's a basic science, right? Amino acids we talk about in our high yield programs. Everybody knows amino acids are one of the cornerstones of MCAT sciences. Then a little bit of reading comprehension. You know, what exactly are we talking about? We're talking about how life came to be, how the small chemicals of the world came to be whenever Earth was just this like primordial soup, essentially, under conditions that simulate that of the beginning of Earth. So that's just more some reading comprehension. So now they're going to discuss how they think that happens. So they said to get to amino acids, malic acid is thought to have formed via hydrolysis of a cyanohydrin intermediate, okay? So hydrolysis is certainly a basic science, and then you can really lean into some of the functional groups and things of that nature. So cyan could be considered one, acids could be considered one. And then they give us this scheme for how malic acid is to have formed. So they give us compound A. It goes through this hydrolysis reaction here, and it turns into malic acid. It looks like there's this intermediate here, and that's what they're saying is this cyanohydrin intermediate. So what is that? It's this guy right here. So reading on, it says subsequent dehydration. Okay, so first we said we were going to add some water to get to this intermediate. Now we're saying we're going to remove that water. So this is all going to go in my flow chart, right? So I'm going to say that compound A becomes the cyanohydrin intermediate, and then it loses water to become malic acid. And then I'm going to say we add water to cut it, right? Hydrolysis, hydrolyze, you use water to create a cut at a bond to get malic acid. And then from there, it says that we take out water and we're going to get to fumaric acid. And it's cis isomer malic acid. So this is actually going to create 2 acids, and that seems very important at this point. They give us these melting points, which to me, here, let me go ahead and write out. Cis malic acid. To me, it's interesting whenever they give me something like melting points, because that immediately makes me start thinking about like bonds breaking and things of that nature. So could they bring that up? Could they give us some kind of graph that discusses the dissociation of these molecules? So moving on, it says ammonia was thought to be a constituent of the early atmosphere. So originally we had some pneumonia just floating around in the sky is what they're saying. And it's proposed that it reacted with fumaric, maleic, and malic acids to afford a pre-biological synthesis of aspartic acid. So the 1-letter code for aspartic acid is D, remember. So essentially what they're saying, and they draw it out in these schemes, so sometimes this flowchart can feel a little bit redundant in a passage like this, but the things that you add are very, very important. So we've got ammonia plus fumaric plus maleic plus malic acid leads to aspartate or aspartic acid. I'll go ahead and highlight that because anytime they give me an amino acid, I'm immediately thinking about, okay, what's the unique way that they can test that? And in our high yield course, we talk about like the 4 or 5 ways they generally test them. So with aspartic acid being a charged amino acid, I'm automatically thinking about its charges, its pKa's, and things of that nature, because those are fair game at this point. So moving on past this scheme 2, which we've already kind of talked about, it says in an attempt to verify this hypothesis, chemists tried to reproduce the synthesis of aspartic acid under simulated primitive Earth conditions. So this is actually very common of the MCAT. A lot of times they will kind of lay some foundational science back work, and then they'll discuss like something that they've observed in nature, and then they're all going to move into this experiment that they did to prove it or justify it. And that's exactly the framework that they've used here. And I've seen tutors teach that like all passages have that if you look hard enough. I don't think that's true, but I do think that it's not a bad idea to be aware that, you know, that's frequently a way that they will structure passages, especially on the CP section. So they observed that we have aspartic acid, and they thought about how could it possibly become, and then they went to the whiteboard and they drew this out, and now they're saying we're going to see if we can actually make that happen. So continuing on, it says an open flask containing malic acid was treated with a continuous ammonia feed, and the mixture was heated at 150 degrees Celsius for 1.5 hours. So they took malic acid and they gave it ammonia, and then they gave it some heat for about an hour and a half. And then they repeated this with a mixture of fumaric and malic acids as well. So that means that they also took the time to put fumaric and maleic acids as well in that. The results were analyzed by paper chromatography. So now we're talking about chromatography. So this is one of the separation lab techniques, and they love to test on these. I'd be shocked if we don't get a question here, especially considering the fact that my eyes kind of jumped ahead and they're giving us like these RF values and how to calculate RF. They're going to ask a question about that. Anytime the MCAT takes the extra time to say something 2 or 3 times, they're almost always going to ask a question about that. So if you feel like they're repeating themselves, they are. Just go ahead and gear yourself up for that question and see if there's any clues within the passage. So we're analyzing it by paper chromatography, and it says that we're going to compare the RF values for the mixture. So whatever these make, that's going to be compared to the standard sample of aspartic acid. So they're pretty much going to take their paper, and they're going to dip it in its mobile phase here, and they're going to add some mixture, so whatever this soup is that they concocted up here, and they're going to add some aspartic acid, and they're going to see how far they run, and if they run similar distances, then it may be arguable that, hey, this is actually aspartic acid. And rather than it like clearly denoting aspartic acid like some of the other separation techniques, what this would do is this would tell you that it had similar properties to aspartic acid. So don't get caught up on that either. You couldn't 100% say this was aspartic acid, but you could say that its polarity was similar, because that's kind of how paper chromatography works, right? So that's it. So here I think the biggest benefit that our flowchart helped us with was keeping some structure, because there's a lot of moving parts here, a lot of different reactions and things of that nature. But I think what's probably going to be most important about all these are these weird intermediate steps. So like the hydrolysis, the dehydration, and all the basic sciences that are associated with it. But let's jump to the questions and see what they thought. So question number 1 says, in the chromatography of the reaction mixture, so they're already asking us about it, water absorbed on cellulose functioned as the stationary phase. What was the principal factor determining the migration of individual components in the sample? So this question is just asking if you understand the concepts of paper chromatography. So let's review those really quickly. So paper chromatography, we talked about, has a piece of paper or silicone gel or cellulose like they described here, and then it's going to be sitting in this beaker that has like some kind of liquid. And the idea is that as the liquid runs up this gel, it will pick up little pieces of the compounds that we have dotted that paper with, and it will actually make them travel. So if you've ever taken like a straw wrapper or like a piece of paper and dipped it in some kind of colored liquid and you saw that it traveled, well, that's kind of a similar principle to what they're going off of here. They're going to see how far the color travels. Now, there's 2 things that are really important here to note, and that is the idea of mobile phase and stationary phase. So it's even kind of mentioned in the question, the stationary phase, it's stationary, so it stays still. And then the mobile phase, it's mobile, so it's moving. So if you think about this, which of these properties is moving? Is it going to be the paper or is it going to be the liquid? The liquid moves, right? So the liquid is going to be the mobile phase, and the stationary is going to be the paper. Now, the important thing about mobile and stationary phases is that they really, really strongly obey like laws of polarity and things of that nature. So if you have a polar stationary phase, like they talked about here, right, because water is incredibly polar, cellulose as well. If you have a polar stationary phase, well, then a polar liquid is just going to stick, or like a polar substance is just going to stay still. It's not going to travel very far. But a non-polar substance would run pretty far. So if you put like some kind of like butter or something like that, I mean, butter's probably a bad example, but something with similar properties, it'd probably run away from it. So the idea here is like that classic mantra, like dissolves like. So if your molecule is easily dissolvable in like the water, it's going to stick very hard and it's not going to travel very far. That's what we're working with. So reading this question, what's the principal factor determining the migration of individual components in the sample? So this question can be flipped for polar versus non-polar. It's kind of, if we're going to reword it, we're going to say what makes something polar, because our phases are polar, right? So they're moving in a polar direction. So what makes something polar? A, hydrogen bonding. Well, little free tidbit about hydrogen bonding, right, is that a hydrogen bond is not technically a bond. A hydrogen bond, rather, is more of like an electrostatic attraction between the partial positives and partial negatives of like oxygens and adjacent hydrogens in this specific example with water. So going off my simplification of what makes these polar, hydrogen bonds definitely does. Solute concentration, how much polar you have does not necessarily determine that, right? So that's not really concentration. Again, that really doesn't play a big impact on this. And the thickness of the paper, you can be dummy thick, but it really doesn't play an impact on your polarity. So the correct answer here is hydrogen bonding, because it has a huge impact on the polarity of molecules. Question number 2 says, what assumption is being made if scientists conclude that aspartic acid was formed by the pre-biological synthesis in the passage? So this one's going to likely be testing less sciences and more just like your reasoning capabilities. So I could rephrase this as which of these has to be true. So answer choice A says aspartic acid is unstable at temperatures below 150 degrees Celsius. So where they're getting that number is that is the heat at which the flask was heated. Now, what happens if it's heated at 149 degrees? I don't know. But we have no evidence to think that it would be unstable if it were 149 degrees Celsius versus 150. That's just the heat that they used. So maybe not A, don't love it. B, all of the malic acid underwent the dehydration reaction to form fumaric or maleic acid. So just generally on the MCAT, I do not like strong answer choices where it's something that says all, because what happens if 50% undergoes the transformation? Do you still have aspartic acid? Because that's what they're asking. Which of these has to be true for us to get aspartic acid? You would still have some aspartic acid, right, if some of it underwent transformation. So I don't like A or B. C, compound A and cyanide were available on primitive Earth. Well, does that have to be true? Well, the statement is saying, can we take these and get to aspartic acid? Well, you would have to have them available to get to aspartic acid, right? So I like answer choice C. And then D says the reaction between ammonia and fumaric acid was catalyzed by the presence of water. Well, water is nowhere in here. It also doesn't even talk about water really being a catalyst. Maybe they're trying to trick you with these dehydration reactions, but they synthesized it here without the mention of that. So I don't think that D has to be true either. So answer choice C is correct. This is one of those where it's like, you read it and you're like, I think it's C, but then you kind of overthink it. Just pick the answer that slaps you in the face. Whichever one you're like, oh my gosh, I would be so stupid if I missed this. That's usually the right answer. Number 3 says, according to the developed chromatography plate. Okay, so this is an example of a thin layer chromatography. What is the approximate RF value of aspartic acid? Okay, so remember our formula for aspartic acid that they gave us here. So it's distance moved by the compound divided by distance moved by the solvent front. So we're going to say compound over solvent front. Now I'm going to glance at my answer choices to see if there's units here, and there are not. So that means I'm just going to get saucy with the math, and whatever works out, that's what I'm going to pick. So it's asking about the RF value of aspartic acid. So for that, we're going to go compound over solvent front. This is another one of those, like, don't overthink it. So we got 1, 2, 3, 4, 5. Aspartic acid looks like it's moved 1, 2. So we're going to say 2 divided by the solvent front right here looks like it's moved 10. So 2 over 10 is equal to 0.20. A is the correct answer. Pretty simple. Number 4 says, which of the following statements does not correctly describe the dehydration of malic acid to fumaric acid and maleic acid? Okay, so remember that is scheme 1. So it's this idea we get from malic acid, and then we get 2 separate isomers of fumaric acid and maleic acid. So which of these is false? The reaction occurs most readily with tertiary alcohols. Let's go back and look at the reaction, because I'm not sure that either of these are tertiary alcohols or that tertiary alcohols were mentioned. And in these not questions, sometimes you have to think about that, and even if you're not confident, sometimes I don't pick it. So we can see here that malic acid is not a tertiary alcohol. The tertiary alcohol means an alcohol, right? A carbon attached to a hydroxyl group would have to be attached to 3 separate carbons. But our malic acid is attached to, looks like 2 carbons and a hydrogen. Okay, so it's actually a secondary alcohol. It doesn't show us that any like tertiary alcohols were used here. But one thing that we do know about alcohols is that generally the way that they will dehydrate is, let me just draw one out here. I have an OH group, and then they have all these others, so tertiary. And generally the way that they dehydrate is the 2 free electrons on this alcohol will pluck some random hydrogen, and now you're going to be left with like H2O sitting on this oxygen, and it's not going to have its valence satisfied, right? So it's just going to donate some electrons, and it's going to move off, and it's going to leave this carbocation intermediate. To have a carbocation intermediate, you think about what makes those stable, and it's generally the ability to create resonance and remain stable through like the donation of additional partial electron charges associated with that. And having more carbons around it means that there are more electrons to donate. So a tertiary is going to dehydrate quickly, or quicker and more readily than a secondary, which is going to be able to dehydrate more readily than a primary. So it goes like tertiary greater than secondary, greater than primary, and that is because of the ability to donate partial electrons. And that donation of the partial electrons is going to allow them to stabilize that carbocation intermediate. Maybe not A, because I would think that a tertiary alcohol would actually like dehydrate really quickly. And the question's asking which of these is false about the dehydration, which could be considered like which of these would make the dehydration more difficult. So maybe not A, but we'll leave it in just because like I'm not 100% sure. B says the reaction involves the loss of a water molecule. It's a dehydration reaction, right? So that one's pretty easy to rule out. C says the reaction has a carbocation intermediate. We just kind of went through that. Like that's just like the way that alcohols dehydrate. So maybe not C. And then D says the reaction is stereospecific. So they actually kind of give this one away in the question stem. If something's going to dehydrate into 2 different isomers, fumaric acid and maleic acid, it's not going to be stereospecific, right? Just like by nature. So the correct answer here would be answer choice D. And then number 5 says, what type of functional group is formed when aspartic acid reacts with another amino acid to form a peptide bond? So this is like something that we explicitly have taught in our high yield lecture series. It's the idea that like it's so important to know the functional groups of amino acids and what a peptide bond breaking and forming looks like. So let's draw that out. So a normal amino acid, just gonna say R, H, COOH, and then it's adjacent to an additional one. None of the other crap is important. carboxylic acid. So it's a dehydration reaction. This hydroxyl will pluck one of these hydrogens off, and then we're going to end up left with a peptide bond that is composed of, and we'll label this C1, C2. So it's going to be composed of like C1 connected to C2, which is still bound to oxygen, connected to nitrogen, which is bound to like hydrogens, etc., C3. And so they're asking what functional group is formed. So let's go through these. An amine. So what's an amine? I actually messed up here. So this is going to be CH2. Right, we got to obey our valences. So an amine is going to be just like an ammonia that's attached to a nitrogen. So this is the structure of an amine, right? And that looks like what we have, or what we had here, right? It's this NH2, it's attached to some other random garbage. So the structure of an amine is going to be an R group attached to an NH2, and the structure of an amide is going to be two R groups surrounding an NH, essentially. And an amide is going to be a nitrogen group attached to an R group attached to like C double bond O. So like almost some kind of aldehyde type deal. Now these really confused me, and so the way that I remember these is amine is a mini and amide is a mighty. Because you can see here that like the amine is tiny, it's mini, it doesn't have a lot of groups. The amide is mighty, it's got a lot going on here. So an amide is what's formed through a peptide bond, and we can kind of see that drawn out here. So the correct answer to this one is answer choice C. That's it for the first passage. Not too bad. Thanks for watching. I'll see you in the next one.